All right, good morning. Through my presentation, I'm going to cover several different aspects of our Loop 345 project in San Antonio, commonly known as FredMed is what we refer to it within our district. I'm going to be discussing the purpose of the project, what lateral bridge slide actually is. This method was actually proposed by the contractor, and there are some reasons why they decided to redesign our contract plans to allow it to facilitate for a lateral bridge slide. Also going to talk about what specific changes were made to the contract plans, the constructability challenges that were unforeseen whenever we started this design process, current construction progress, and lessons that we learned along the way. This project is located on the northwest side of San Antonio. When the project's completed, it's going to provide a direct route into the South Texas Medical Center. And that's really the driving force on this whole entire project is that's a very important, vital lifeline to San Antonio. And we have a lot of bottlenecks coming into the medical center, and we're trying to get things to where they're flow a little better, and we're potentially talking about life or death. There's three main arterial routes that go into the medical center. From I-10, you can go in on Wurzbach Road or Medical Drive. The problem with Wurzbach Road is it has 4 different traffic signals that emergency vehicles would have to go through, whereas the Medical Drive, once this project is completed, will only have 1 traffic signal. So it's going to be a huge improvement on the way that we're able to access our South Texas Medical Center. Little history on this project. This project was previously let with a different contract, and it was awarded to a different contractor. Fortunately, that contractor, I say for the department, fortunately, they ended up going under before they got this project started. So the department dodged the bullet of starting this job on a default. So the department relet the job. We had significant delays in getting the package put back together, getting it relet and awarded to a new contractor. Whenever we re-put the contract plan set together, we actually cut the time the bridge construction was allowed on milestone 1 by a third. So that was a very big change to the game plan from what the original contract plans and how they were designed. The main purpose was we really wanted to encourage the contractor to come up with new innovative ways to accelerate the bridge construction process. The existing traffic signal, or the existing intersection before we ever started construction, it was just a traditional signalized intersection. Fredericksburg Road is a 7-lane typical section. It has a ADT of 63,000 cars a day. And Medical Drive, it's on the far east side is actually a 3-lane section. It widens out to 4 lanes, but just west going into the medical center, it has an ADT of 25,000 cars per day. We will be, when this project is completed, we will have the intersection converted to a diamond configuration. We're going to have 4 different main lanes that are going to be a depressed section that's going to go underneath the existing Fredericksburg Road, and you're going to have 2 frontage road lanes going inbound and outbound to the medical center. That's going to be very instrumental to eliminating the choke point at this particular intersection. The bridge that we're constructing across Fredericksburg Road, with it there not being a bridge there at all, the bridge is only 64 foot wide going across, but it's 180 foot in the other direction in actual width. So the span length is significantly shorter than what the width of the structure is. The original contract plans called for this bridge to be installed utilizing precast abutment segments, and then installing box beams in a side-by-side configuration, and then finally casting a 5-inch slab across the whole top of the bridge. It was a very tall order to ask from the contractor to do that operation in 14 days. Contractor actually came back later and they said that they felt that it was going to take them 21 days, and that's the way that they bid the job. At the beginning of the project, the contractor approached TxDOT and requested permission to redesign this bridge and project to make it compatible with the lateral bridge slide. And that brings us to what is an actual lateral bridge slide. And this is an accelerated bridge construction method that allows for the bridge superstructure to be cast in an offline position out of traffic and then moved into place once all the superstructure is constructed, cured, and reaching design strength. As with anything, there's pros and cons to utilizing various methods of construction. Biggest advantage on this one with the bridge superstructure being cast offline is that we do not have any, necessarily we eliminate the risk associated with construction that if we have a bad cylinder break, that we're sitting there and we got a roadway closed down and we can't open it because we haven't reached our design strength that we need to allow traffic to pass. Another big advantage that we have on it is that it reduces the time that the roadway actually is closed. The original contract on this job, we were looking at 14 days to construct this particular bridge. And with the lateral bridge slide, we're hopeful that we will be able to have the bridge installed in less than 3 days. So with this being in the medical center and having to coordinate all the efforts and everything with all the various emergency response partners, this is a very big task, and this is very rewarding that we could possibly give them this bridge in a reduced time frame. Another advantage that is seen being used in other states with the lateral bridge slide, I was very fortunate to be able to go up to Michigan and see how they're doing with their lateral bridge slide program. They slid their first bridge in their state's history back in August, and then they've got another one set to happen later this next month. What they're doing is they don't have frontage roads up in Michigan like we have in Texas, so the detour routes that they're having to utilize whenever they're replacing the bridges across these interstate highways sometimes is in excess of 30 miles. So they're actually installing the temporary piers with additional capacity on the side, and they're building the proposed bridge superstructure on top of the temporary supports and detouring traffic onto that while they demo the old bridge, get the new superstructure or substructure installed, maybe do any retrofit that might need to be done if they're reusing existing substructure elements, and then the only closure that is really experienced that they have to use the extensive detour would just be the time that they're using to slide the bridge into place. Biggest disadvantage of this particular operation is that it requires a lot of additional structures, elements. You have to build an entire temporary bridge substructure off on the side and to support the bridge and while it's being constructed, and then that later has to be removed after the bridge is placed in its permanent bearings. Michigan was telling me that their costs that they're experiencing on these temporary structures in conjunction with the actual slide cost itself is in between $1 and $2 million. So it's really not a cheap operation to run, but it does have, in a road user standpoint, is very effective to reduce road user cost. Now, if it costs that much money, why in the world would any sane contractor want to utilize this accelerated bridge method? On our particular project, it has several milestones with incentive and disincentives. Milestone 1 is specific for the bridge construction. We only allow the contractor 14 days to construct the bridge, but if they want to earn a maximum incentive, they have to do it in less than 8 days. Their incentive disincentive costs to $15,000 per day. And then in addition to that, the total project itself has a milestone for substantial completion of the project. We're allowing a contractor 400 working days to fully construct the project with the maximum incentive if they completed 20 days early and 380 days. Disincentive costs for extending the project past the 400 working days would be $6,285 a day that they don't finish the job on time. So with the risk and with them having already bid the job with 21 days to build the bridge, and the other key thing that makes this a little more effective for the contractor is the fact that our depressed section has drill shaft walls on either side of it. So we already have the foundations in place that we're paying a contractor to put in, and they're able to capitalize on that and utilize those to make this operation a little more cost effective. There's several proprietary systems that are utilized to move bridges across the United States. Most of them use rollers, tracks, or Teflon coated surfaces to reduce the friction whenever they're sliding the bridge into place. The actual system that our contractor is using is designed by Hugh Boyle Engineering out of Salt Lake City. His system utilizes Teflon-coated elastomeric bearing pads and stainless steel plates to provide a low friction sliding surface. The plates and stuff are actually going to be lubricated with dish soap, so we're technically sliding the bridge on Dawn dish soap and Teflon. Duodeck bars are going to be utilized with hydraulic jacks to propel the bridge from the temporary location into its permanent spot. The bridge structure itself, the entire superstructure weighs 4 million pounds, but it's constructed in half, so we're going to be moving 2 million pounds at a time. The estimated force that we need to move this bridge sideways is going to be around 90 tons, and that's a little bit on the high side. Nobody really knows what the exact friction of the in between the bridge and the sliding surface plane on what it really is going to be. So with this particular firm, they've done about 30 different bridge slides, and they have a wide range of low and high end. This is figured toward the high end. It's spec'd out using two 60-ton jacks, which provide 120 tons. So we really automatically have an additional 25% load that can be used to get the bridge broke out and moving. That's where the initial force, your biggest part of your initial force, is just trying to get the bridge in motion. Once you get it moving, the friction value goes down significantly, and it's a lot easier to move. This particular system, it has redundancy built into it. We have additional ducts built into the abutment along with additional bars installed. This allows us, in the event that we're unable to move the bridge with 120 tons, we can put two additional 60-ton jacks on there and we'd have 240 tons capacity. And it also serves as a backup that if we break a bar or something happens, that we can move the jacks over to the other duct and continue on with the slide. I think it's any of the states that have done this that I visited with, it's kind of an industry standard that you want to make sure that you have redundancy in your sliding system that's being used to move the bridge into place. Now, I'm going to move on to what was actually designed to make the bridge slide in reality. The green in this picture represents the bridge in its temporary location. You got a drill shaft wall on either side that the abutment's resting on, and whenever we get ready to slide the bridge is going to be slid straight across 160 feet until it gets even with the yellow and blue blocks. The blue represents the little area that overlaps between where the bridge actually is and where it's going to be whenever it's done. As far as we have been able to find out, this is most probably the widest structure that has ever been laterally slid in the United States to date. Most of the bridges, they're 4-lane sections. They build it on one side on a freeway, and they slide it into place. Very rarely are they ever trying to move the distance that we're moving. The system that we're using with the post-tension ducts within the abutment, it kind of acts as a string through a straw. When you start pulling on it and you're sliding the straw over the top of the string, it basically is going to help kind of line itself up, and it's going to want to drift itself naturally to the anchor point where we're pulling from. The first major redesign that was done was on the drill shaft walls themselves. The drill shafts were all lowered 7 feet to facilitate the bridge superstructure in the temporary location. The orange color is the actual surface that it's a slab that's 2 foot wide. We call it the slide slab, and that's the supporting surface that allows that supports the bridge in temporary location and throughout the entire slide. And the best description I can give you for this, it's like 2 train tracks that are going from one end of the bridge in a temporary location all the way through the intersection to its permanent home. And this is essentially going to be the roadway that the bridge is going to be moving on whenever we do slide it laterally. The purple is the actual anchor block that's going to be used in the event that we have to back the bridge up. That's another added redundancy feature that is part of this system, that if we're pulling the bridge into place and one side gets too far out from the other and we actually lock the bridge up in between the 2 abutments, that we can actually back it up and we can straighten it out and try to pull it forward again. So from an owner standpoint, that's a feature that we definitely wanted to see, is that we have the ability to move it backwards and not just only forwards. Whenever we go through the middle of the intersection of Fredericksburg Road, the colors on all these plan sheets, they all correlate to each other. So as I move through it, you'll start seeing how the pieces are going to start coming together. The orange is the slide slab, and the pink, we actually built a back wall, retaining wall that goes through the middle of the existing roadway. And what that's going to do, it's going to allow us to shore up the roadway excavation while we're doing the actual lateral slide. And then it's going to also function as a traditional abutment does in the state of Texas when the bridge is actually in place. Slide slab and that back wall, I mean, that's rigidly fastened to the drill shafts, and that's going to be the closest analogy I can give you on this is actually going to function as the bridge abutment. I use the term abutment in this presentation, in this system, loosely, because what it is, the abutment is actually part of the superstructure and not the substructure. That terminology often confuses people, and it clouds up the actual vision of what is happening whenever we're doing a slide. The key feature whenever we are redesigning this bridge to a lateral slide is the actual abutment design itself. The abutment is actually a semi-integral abutment, so it is rigidly fastened to the beams and to the bridge deck. Now this is important because it allows for the bridge to be moved and eliminates the risk that the abutments are going to twist and rotate and get out of square whenever we're pulling the bridge into place. The red on the top, that represents a pour that's done separately. There's actually a construction joint on top of the green block. The green block is where the beams are going to be set, and then the red is going to be like a back wall that actually ties the bridge deck and the beams into each other. There's several little boxes that are kind of pink in color, and then you got 2 blue ones, and those are the sliding shoes and bearing shoes that hold up the whole entire weight of the bridge whenever it's in its temporary and its permanent home. Whenever we go to jack the bridge up and move it into place, we're going to be utilizing only the blue blocks. And we're going to take Teflon pads, and we'll insert the Teflon pads underneath the blue blocks, and we'll just keep, every time we advance the jack forward, we'll go ahead and we'll keep moving it one after another like we're rolling it on top of pipes. Here's a typical section that shows the bridge abutment. As you can see, it's rigidly fastened to the top, and it actually has a construction joint right here that you'll see later. This is various layout of how the bearing pads are going to be put under the bridge whenever it's in its permanent location. Now, I'll move on to constructability challenges. The biggest issue is that the contract plans only allow the contractor to build the bridge only have nightly lane closures outside of the milestone. All the lanes must be open all the time during the day in time for the morning commute. And then whenever we reduced the drill shafts by 7 foot, the drill shafts were supposed to be utilized to shore up the excavation. So we had additional shoring that had to be installed there. The first challenge was trying to build the slide slab through the middle of the intersection in advance of the bridge slide. The contractor came up with the concept of utilizing trench boxes with the trench cover. The cover uses I-beams and roadway plates, which allows you to uncover it at night, do what you need to do, cover it back up, and run traffic over it during the day. In the temporary bridge location, the contractor opted to use a gravity wall built out of flowable backfill. As you can see, this is in advance of us actually splitting traffic to the next phase around the work area. But they got in here and they were actually able to get in and start doing some of the bridge abutment work in advance of completing phase 2. This is our construction progress starting at the beginning. We used the trench box cover and the trench boxes to install the drill shafts through the middle of the intersection. And we later came back and followed it up with the slide slab and the back wall. This is in the temporary work zone. We used speed shoring against the flowable fill back wall. The speed shoring right there, it was braced off of it. Once we got the drill shafts cast, we went ahead and we excavated it out and sloped back, and we started construction of the slide slab. This is actually the first day that we started construction on abutment 1, and it's actually segment 1B. It's the one half of the abutment. The first step that they did was started to form up the actual pedestals that the bridge abutment will rest on. Then they had to build a deck to support the concrete while it was being cast. In this picture, you can see the 2 4-inch ducts that were installed throughout the entire length of the bridge abutment that will be utilized in the slide. And then we finally moved on to pouring concrete on the abutments. Now we got the construction joint here. We just poured it up enough to put the beams on it at this point, and the rest of it will still be advanced up at a later point in time. Once we got the abutment 1 on one side and we got traffic split around on either side of the work area, we're able to start construction immediately on the slide slab for the other side and start working on the second abutment. Here you can see I'm tying steel for abutment 2, and then we have finally got both abutments cast on it. Next big milestone that we had was setting beams on the project. Utilizing the box beams, it went fairly quick. We were able to get the beams down into the actual work zone and have 2 cranes swing around and place the beams. So we were able to do that work without impacting traffic at all. And we actually did it in the middle of the day versus an operation like this, which would traditionally be done at nighttime to avoid traffic impacts. After we got all the beams placed, you can really kind of see the bridge start taking place. And that's where we started kind of getting awkward looks from all the general public as they were driving through, and they're going, hey, the bridge is supposed to be over there, not over here somewhere. Once we got the beams, you can kind of see underneath. This gives you a little better idea how the slide's actually going to work. You got the 2 ducts where you got 2 duodag bars that go through. This is steel for the anchor block that was cast at a later point in time. Now, right this interface between the slide slab and the pedestals, that's where you're going to put the Teflon pads, and that's the surface, that interface where the slide's going to be occurring. We moved on to installing the shear keys on the bridge. The contractor opted to pour the shear keys separately, and then we advanced onto the bridge deck. Here you can see that we have the construction joint for the bridge deck pour. Actually, it's several feet off the edge. It's about 5 feet off the side. The importance in this is whether we transverse or longitudinally screw the concrete like we did in this application, you want to make sure that you preload all the beams and you get all the deflection that you're going to get out of the beams down before you make that connection on the integral abutment here on this side. Because what will actually happen is you'll induce forces, internal forces into the structure that we don't want to be there. So whenever you're tying the bridge deck into the ends, you want to make sure the concrete's plastic whenever that's happening, and that the beams are fully deflected. Further pouring the bridge deck, it's just the center segment. Lessons that we learned throughout this project, with the project previously being let with the contractor ordered the beams immediately, so we already had the beams on stack, and the contractor agreed to utilize the box beams from the previous contractor. So if they would have opted to not utilize those beams, they could have redesigned the structure as an I-girder structure. Now, the importance in that, whenever we're doing a slide slab, is that we would have reduced the slide weight that we were working with. We would, on a 4 million pound structure, we would have reduced it by about 20%, or 790,000 pounds. And it also would have reduced the structural cost by about $250,000 based on our current average bid pricing. The other thing is that we want to make sure that we're utilizing slide hardware and systems that have redundancy built into them, or that the contractor has the ability to make repairs to the system in a timely fashion whenever we start the actual milestone. And then one thing that the contractor didn't estimate is they said that it actually took them quite a bit longer and quite a bit more money to install the slide slabs through the middle of the roadway and to perform the other shoring necessary to make this application work. And the way that the deal was made on this, the contractor was allowed to redesign the project, but they could not increase the project cost at all. So all those costs that were extra would have to be absorbed by the contractor. So that concludes my presentation. Does anyone have any questions?